Good afternoon, everybody. Let's get started with the class. For announcements, you have a few assignments due in the next few days. Quiz 3 is due tonight. Quiz 4 is due on Friday. We have a lot of these quizzes up early in the class because they're the kind of the basic material that you need to do the later material. So I want to make sure you have a solid foundation and then answer any questions you might have on that material. Homework 3 is due on Tuesday, and that's going to be completing the material for the exam. Exam 1 will be Wednesday, the 12th, and that will be held during this class time. So what I'm going to do is I'm going to start up a Zoom session. I encourage you to join the Zoom session. It's not required, but that's how I will communicate any responses to any comments or questions anybody has. That exam will cover through Thevenin equivalent circuits and maximum power transfer, which we will cover today. So it'll be during class. You'll have this 30-minute grace period after class. So 4:40 to 5:30 is the exam period, and then you have until 6 p.m. to submit your exam. So you get a little extra time for that. And then you're going to scan your exam and submit it via Canvas, and that's it. So you have to work alone. It's open book, open notes. You can use MATLAB if you want. Use your calculator. And so I will send an announcement with some details on that. You'll see everything that's printed on the front of the exam, all the rules. I'll send that out via a Canvas announcement. There are review problems and practice problems. So the review problems are some earlier exam problems. They're posted on Canvas, but also see what I call practice problems for material. Those aren't exam problems, but they're sort of tutorial problems that get you up to speed if you want to try easy problems or harder problems there. So take a look at those. And there's also a Slack channel set up for the exam that you can post questions to. So someone says, are we allowed to ask questions about the quiz during office hours? Absolutely. Yeah, please stop by office hours. Let's talk about the quiz. And someone asks about accommodations. So I'm going to send an email out about that, and probably 2 options for times there that involve that period. Either by default it'll go later, but I'll send that out in the announcement as well. Okay, so yeah, if you have any other questions about the exam, anything comes up in your mind, stop by office hours. I'd be happy to answer those questions. So I wanted to do a preview of Lab 3. So Lab 3 is all about resistive circuit analysis. You're going to build this circuit on your breadboard in Lab. And this circuit is set up perfectly for node voltage analysis. And so you're going to perform node voltage analysis during the pre-lab, and you'll get your calculations. And then in lab, you're going to measure the node voltages and compare to your calculations. And you're going to see that power supplied by the source equals power absorbed by all the loads, the resistances in the circuit. So this circuit here has a voltage source attached between ground and one of the node voltages. So that gives you one of the node voltages right away. You do not write a KCL equation at that node because you know that voltage. You write a KCL equation at the other nodes. So give that a try. Let me know if you have any questions about that at office hours. The circuit is also set up very well for calculating and measuring the equivalent resistance of the circuit. So if you look at the circuit, you can combine, let's see, R2 and R3 in series, but then you're kind of stuck. You're not going to get very far trying to combine resistors in series and parallel to figure out an equivalent resistance, right? So what you're going to wind up doing is going back to how we started the discussion on equivalent resistance. You're going to, in lab, apply a voltage, figure out the current, and Ohm's law gives you the equivalent resistance between those two terminals. And then when you calculate, with outside of lab, you can apply a voltage and calculate the current and voltage over current is the equivalent resistance. So that's how you'll have to do that here. Okay. So that's a quick preview of that lab. And I'm going to jump next back into Thévenin equivalent circuits. All right. The Thévenin equivalent circuit. This was a way to take a complex, a little more complicated circuit with resistors and sources and linear sources, dependent or independent, and create a very simple equivalent circuit for the purpose of easier analysis or just giving a characterization of the circuit to someone so they know when they connect a load to it, how much current and voltage will there be at the terminals. Okay, so let me get my arrow here. So if you have any linear circuit with resistors and sources, then it's equivalent to, or you can calculate an equivalent to that circuit. That is called the Thévenin equivalent circuit. The Thévenin equivalent circuit is a voltage source and a resistance. And you can show, we talked about last time, that if you connect a resistor to these two terminals, you wouldn't be able to tell the difference between these two circuits if they are equivalent. So these circuits are equivalent from the perspective of anything connected to terminals A and B. If I put both of these in a box and I've calculated the Thévenin equivalent properly, then if I give you a voltmeter, an ammeter, a voltage source, a current source, and you connect things to terminals A and B outside the box, you wouldn't be able to tell the difference. So what's the value of this? Why do you care? Well, one reason is this. Suppose you're doing an analysis of a circuit. So suppose you have this circuit, it's a linear circuit with resistors and sources, and you need to calculate the power delivered to a load. So you connect a load resistor R sub L, and you have 5 different load values, and you want to calculate the power delivered to R sub L. And then this is the circuit. It looks something like this. You have this really complicated circuit. And 2 terminals are exposed from that circuit. That's where you would connect a load. Okay. So if you had 5 resistor values, you connect the first here, you analyze this whole relatively complicated circuit, and you get a power value. And then you attach the next resistor. You've changed the circuit when you've attached the second resistor, right? And analyze the whole circuit again, and the third resistor, fourth. So you'd have to analyze the circuit 5 times. Instead, you could analyze that circuit. You still have to analyze that circuit once, but instead of applying that resistor, you analyze that circuit to calculate the Thévenin equivalent. So now this circuit, from the perspective of whatever's connected to the terminals, is equivalent to this more complicated circuit. So instead of analyzing this circuit in the lower left 5 times, you would just analyze the circuit in the lower right 5 times. This would be a lot easier. So you can't get out of analyzing this more complicated circuit once in a way to get the Thévenin equivalent. But then I sure would rather work this circuit in the lower right 5 times because it's a lot simpler. Okay, so that's a use of the Thévenin equivalent. And another use, as I mentioned, is you can characterize this circuit. I don't have to give people the details of the circuit if they're just going to connect things to it. I can give them the Thévenin equivalent, and they can connect or connect resistors or other circuits to the terminals and do an analysis just using the simple circuit, or just understand the circuit, how it behaves between terminals A and B with the Thévenin equivalent. Okay, so that's the motivational speech. Let's see. So someone asks, why would you analyze it 5 times? Well, I have 5 different resistor values, R sub L, in the lower left, right? So if this is 10 ohms, then I'd have to analyze the circuit and I'd have to figure out, well, what's V squared over RL, or what's I squared RL, or what's VL times IL. I'd have to get VL and IL and figure that out for power delivered. If I change RL to the next value of 5 values, then I have to analyze it again. So yeah, I'm changing RL. You know, a practical example is, let's suppose I have an amplifier and I'm trying to figure out, do I want to connect a 4 ohm speaker, an 8 ohm speaker, a 16 ohm speaker to that amplifier, which will give me maximum power delivered to that speaker. You could not use the whole circuit, the actual circuit of the amplifier. You could just use the Thévenin equivalent circuit if you had that. Okay. So great. That's why you would use the Thévenin equivalent. How do you calculate the Thévenin equivalent? Well, I like to say you do this. You write the answer and you fill in the blanks, right? So this is the easy part. Every time you're asked to calculate a Thévenin equivalent circuit, first draw this, right? That's going to be the answer. And then you need to calculate VT and RT. Okay, so that's step one. Step two is, well, let's figure out what VT is. Let's find the Thévenin voltage VT. And so here's that circuit, complicated circuit. And to figure out what VT is, remember we defined VT equal to VOC. VOC is the open circuit voltage. So that means don't connect anything, or equivalently connect an infinite ohm resistor and figure out what is VOC. So the Thévenin voltage equals the open circuit voltage between terminals A and B. Okay, so leave it open circuit. Don't connect anything to those terminals. You have some circuit in here, resistors, sources, and then you have 2 wires sticking out. Figure out what that voltage is, and without connecting anything to those terminals, and that's VT. So then you fill that number in right here. Then you find RT, and there are 2 ways to find RT. There's the kind of direct way, brute force way to do it, and then there's a little smarter way if you know something about that more complicated circuit. Okay, the general way, what I called the brute force way, the general way is RT equals VOC over ISC. If you go back a lecture, right, this is how we defined RT. We said it's VOC over ISC. Now you have VOC, right? You've just calculated that from step 2, and that's equal to VT. So now you need to figure out what is ISC, the short circuit current. So that means apply a short, a wire, between terminals A and B, okay, and figure out what is the current flowing from A to B through that wire. And that is ISC, right? That's a 0 ohm resistor connected to terminals A and B. So when I showed that plot of voltage versus, what was it? Current versus voltage versus current, one of those, you saw that when you had voltage equals 0 on the axis, then that was the ISC value. It just means connect a short and calculate that. Now, you've changed the circuit. When you add that short, when you apply that short, you've changed the circuit compared to step 2 here. So you have to reanalyze the circuit to figure out what that current is. Okay, so now you're done. You have RT, VOC over ISC. You have VT, you're done. And now this circuit in step 1 with the values plugged in is equivalent from the perspective of anything connected to A and B. It's equivalent to this more complicated circuit. I mentioned there are 2 ways to calculate RT. Here's the second way. This is a special case. If the circuit, this original circuit, has only independent sources, okay, that means circles, no diamonds, right? It does not have any dependent sources, current sources, voltage sources. There's no diamonds. There's only circles. Set all of the sources to 0 and then calculate the equivalent resistance. And the equivalent resistance between terminals A and B is RT. Okay, and I'll show you how that works, but you can do series and parallel combinations if able, and calculate RT that way. That's usually easier than step one. So if you have only independent sources, I would go right to step two. If you have any dependent sources in your circuit, in this more complicated circuit, then you have to do step one. Okay, you can't just zero out that source, that dependent source, and calculate the equivalent resistance. But if you have only independent sources, what you do is you're going to set all of the voltage sources to zero, all of the current sources to zero, and then just like you did in your homework, between these 2 points in the circuit, these 2 nodes, you're going to calculate the equivalent resistance, and that's RT. Okay, so this slide is good guidance for what do you do when you encounter a Thévenin equivalent problem. Now I have to expand on number 2 here because, well, wait a minute. If I set all my voltage sources to zero and current sources to zero, what does that even mean when I have 0 volt and 0 amp sources and then I try to combine in series and parallel? Here's what that means. Okay. If you have a voltage source set to 0 volts, because it used to be 4 volts, but you're trying to calculate the Thévenin resistance. You have only independent sources. You're setting that voltage source to 0. You can replace a 0 volt source with a wire between those 2 terminals. Right? Left and right of these equal signs are both ways to cause 0 volts to happen between 2 terminals. So just replace all your 0 volt sources with a wire. For your 0 amp sources, okay, how do you make a 0 amp source happen? Simply, you just pull that source out, right? Both on the left and the right of both of these circuits, right? On the left and the right of this equal sign will cause 0 amps to flow. A break in the circuit or a 0 amp source causes 0 amps to flow. Okay, so you can replace all your 0 amp sources that you zeroed out to calculate RT. You can replace all those with opens. Okay, so now since you had, if you're using this technique, a circuit that had only resistors and independent sources, and you've replaced all those independent sources with either shorts or opens, now you're left with just resistors in that circuit. And then you can use series and parallel combinations, if able, and calculate the equivalent resistance. Okay, so to calculate the Thévenin resistance when all the sources in the circuit are independent, the first thing you do is you replace all the independent voltage sources with shorts. Just draw a wire. Replace all the independent current sources with opens. Just remove the source. Okay, and then calculate REQ between the terminals. Okay, we'll do an example of this next. So I'm going to show you what this means exactly. Okay, and then you wind up with this Thévenin equivalent that is a voltage source in series with a resistor, and you can use that as an equivalent for future analysis external to that circuit when you connect components or subcircuits externally to that circuit, to those 2 terminals. All right. So let's switch over to the whiteboard and work an example. So a typical problem would look like this. There's going to be a schematic, and it's going to say find the Thévenin equivalent. So let's create a circuit here. let's define a circuit. So I have a voltage source. Let's make that 12 volts. And then I have some resistors. And then a pair of terminals. And let's put some values in here. 10 ohms. Let's put another 10 ohm resistor and a 40 ohm resistor. All right. So step one, when you're finding a Thévenin equivalent of this, is to, well, write out the Thévenin equivalent, draw the schematic. So plus, minus VT and RT. That's what we're looking for. Okay, step two, find VT. Okay, and remember, VT equals VOC. Okay, so what I'm trying to do here is calculate the voltage between these two terminals without connecting anything externally to the circuit. Just figure out what is that voltage, and that is VOC. So once I find that voltage, that's VT, I can write it here. Okay. So there are at least a couple ways I could solve this. There's usually one or two or three multiple ways to solve for a voltage like this. When I look at this circuit, I see 3 series resistors, right? The current that goes through this 10 ohm resistor also goes through this 10 ohm resistor. No current leaves terminals A or B, so all that current from the 10 ohm resistor goes down through the 40 ohm resistor. If the same current goes through 3 resistors, those 3 resistors are in series. And I'm looking for the voltage between A and B, which is the voltage between the A node and the B node, right? That's VOC right there across that resistor, that 40 ohm resistor. Remember, voltage exists between nodes. So I'm looking for the voltage between this whole top node and this whole bottom node here. So I have that drawn here between the terminals, but that's also the voltage across that 40 ohm resistor. Okay, so I have 3 series resistors, and I want the voltage across one of those resistors. That's set up perfectly for voltage division. Okay, so let's use voltage division. So VOC, the voltage across that 40 ohm resistor, equals the voltage across the series set of resistors, 12, times the ratio of, on top, you have the resistance across which we're trying to find the voltage, and then in the denominator on the bottom here, the sum of the series resistors. And so that's equal to 8 volts. Okay. So then I come over here and I write 8 volts. VT equals 8 volts. Okay, other ways you could solve for this 8 volts. I could say, well, I have some current IX going around this circuit. The voltage across this resistance is 10 times IX, 10 times IX, 40 times IX. Find IX. VOC is 40 times IX. Right? You could do that too, but this is a shorter way to do that. So various ways to do this. Okay. All right, so we have solved for half of these variables. Let's solve for RT. When I look at the circuit, I see I only have an independent source. I have no dependent sources. Right? I could have more sources in here, but they have to be all circles, no diamonds. They have to be all independent. So since I have only an independent source, I can use approach number 2, where you calculate the equivalent resistance between the two terminals after you've zeroed out the sources. Okay, so what do I mean by that? Let's zero out that 12-volt source. Right, so that's 0 volts right there, plus, minus 0 volts. Right? And then I have a 10 ohm resistor, another 10 ohm resistor, and a 40 ohm resistor. Okay. And so I want to figure out what is the equivalent resistance, REQ, between terminals A and B. Okay. So note here, let me just draw this in. Remember what equivalent resistance means. It means like I'm applying an ohm meter right here. I'm going to draw a box with an ohm in it. It's like I've applied an ohm meter right there. And what an ohm meter does is it actually applies a voltage, right? It applies a voltage. It measures the current and or applies a current, measures the voltage, either way. And it calculates V over I, and that's REQ. So when you're calculating the equivalent resistance between terminals, you have to visualize this because that helps you visualize our circuit elements in series or parallel. Okay, for example, well, we can recognize that these two 10 ohm resistors are in series because the same current goes through them, right? So those are in series. 10 plus 10 equals 20 ohms, right? And we could also recognize that, there's that 20 ohm resistor there, that this 40 ohm resistor connects to the same two nodes as that 20 ohm resistor, right? So here's node A. I'll call that node A up top. This 20 ohm resistor, I'm imagining this combined into one resistance. This 20 ohm resistor is connected between A and B, right? This is node B here. The 40 ohm resistor also connects between nodes A and B. So they are in parallel. So REQ equals the 20 ohm resistor. I'll just write 10 plus 10 to show where that's coming from, right? That 20 ohm resistor in parallel with, I'm just going to write parallel, like two parallel lines. That just means do the parallel combination calculation in parallel with 40 ohms. And if you do that, 20 in parallel with 40, you get 13.3 ohms. Okay. And so you can put that here, 13.3. And so we're done. We're between, I should write my terminals here, between terminals A and B. This is the Thévenin equivalent. If I were to connect anything to these terminals, a voltage source, a resistor, current source, you would see the same relationship between voltage and current as you would here. Okay, so if I connect something here and I connect it here and you put both of these in a box, two different boxes, you wouldn't be able to tell the difference between them in general. So someone asks, voltage voltage division is VS times R1 over R1 plus R2 plus R3. Yes. Yes. So, but we're trying to, if you call this resistor R1 here, then voltage division says in the numerator is R1 and in the denominator is the sum of the resistances, right? If you call that R3, then it's R3 over R1 plus R2 plus R3. Mhm. Oh, yes. Oh, this is a good question. Why was the 40 ohm resistor in series when we found VOC, but in parallel when finding REQ? That's a really good question. Okay, because if I draw these circuits separately, uh, this is I have some 12-volt source. Oops, right? I don't think anyone would argue that anyone would question that these resistors are in series because the same current goes through them. So what current is that? It's the current coming out of the source. It's going through this resistor, this resistor, this resistor back to the source. That's the current path. So this same blue current goes through all three resistors. Those are in series. Down here, if I were to draw that again, I've actually I'm looking at the circuit differently, or I'm actually changing the circuit. I have removed that voltage source, and now I have 10 ohms, 10 ohms, and 40 ohms. And this ohm meter actually looks like a voltage source. Okay, so if I apply, let's see, what variable can I use? Vx, and I measure Rx. It doesn't matter what Vx is. You can make it 2 volt, or Ix, not Rx, Ix. It doesn't matter what Vx is. You can make it 2 volts, you can make it 10 volts, you can make it 100 volts. It doesn't matter. Pick a number, calculate Ix, and Req equals Vx over Ix. Okay. That's what you're doing when you're calculating equivalent resistance. Okay. But let's look where this Ix is flowing. This Ix flows and it splits here and here, right? In fact, let me even make this a different color. I should have 3 different colors here. That Ix in blue splits into this red current, right? And this green current, which have different values. So in the top case, we had the same current going through 10, 10, and 40. In the bottom case, we don't have the same current going through the 10, 10, and 40. We have this Ix splitting into red, splitting into green, and then combining back into the bottom into blue. Okay. So, these are just different circuits. They're the same base current, but you're looking at different variants of those. When you're calculating the Thévenin equivalent, calculating the resistance, you're actually applying a source over here on the right. And when you're calculating, let's see, the voltage VOC, you don't have a source over here on the right. You have this 12-volt source. So they're different circuits. Okay. Okay. Let me back up a step. I showed you the second way on the previous slide, the second way to calculate the Thevenin resistance. And so now I want to go back and say, well, what if we don't want to do this? What if we either didn't recognize that we have only independent sources, and that would be probably easier. Let's calculate RT again, right? This here was find RT. Let's do find RT again, but using the first method, where I said you have to calculate the short circuit current. Okay, so we have a 12-volt source. I'm going to redraw this circuit so I can modify what's connected to the output. Okay, so I have this circuit here. Here's terminal A and terminal B. I already have VOC, but now what I want to do is I want to short the output like that, and I want to calculate ISC. And then RT is equal to VOC over ISC. Okay, so let's do that. What is this current? Now I can't reuse this circuit on the left because I've changed the circuit. I've added a short there. Okay, let me just start looking at the circuit and see what I see, right? So what I notice here is this. Since I've applied a short across terminals A and B, this is 0 volts. Okay. I have 0 volts between this I'll call it terminal here and this terminal here. That also means I have 0 volts across that 40 ohm resistor, right? I mean, look, if there's 0 volts between A and B, then there's 0 volts between this side of the resistor and that side of the resistor. Okay. In fact, I've joined these nodes and created one node. I have a resistor connected. Both sides of that resistor are connected to one node, same node. So there's 0 volts across it. If I have 0 volts across a resistor, then I have 0 amps through that resistor. Ohm's law, right? So I have no current going down through that 40 ohm resistor because there's 0 volts across it. I know going this way, right? If I look at that path, I have the current ISC. If I have ISC going to the right and 0 going down, then that means that this current here is also ISC, right? ISC goes through this resistor, 0 goes down, ISC continues on, that's ISC. Right? This is ISC. ISC. And what I could do now is I'm looking at this and like, how do I find what ISC is? I think I can do that with a single KVL equation. Why do I say that? Because I recognize that right here across this 10 ohm resistor, I can write a term that is I times R, right? ISC, if you can read that, that says ISC times 10, right? I times R. Against this, oh, that should be a minus right there. Should have drawn this bigger. So across this resistor, I have ISC times 10. Across this resistor, I'm going to draw the plus down here and the minus over here. Across this resistor, I also have ISC times 10. So that says ISC times 10, that says ISC times 10. So I can relate the voltage across these resistors to ISC. Now I'm going to write a KVL equation, and that equation will look like this. Let's just start here and go around this way. Minus 12 plus 10 ISC, right? Plus 10 ISC around here, back to the starting point equals 0. So I get 20 ISC equals 12. ISC equals 12 over 20 equals 0.6 amps. So if I take this circuit on the left, the original circuit, I apply a short between A and B, I will have 0.6 amps going through that short. That's what this is showing. So that is my ISC, but I want to calculate RT. RT is equal to VOC over ISC, which is equal to, it's VOC, 8 volts. 0.6 is ISC. So that's 13.3. Right? So you get the same answer here. Okay. So this shows the other way. This was the number two way. That was the number two way. This is the number one way on that previous slide to find RT. You can always do this. This works if you have dependent sources, independent sources. They still have to be linear resistors. You can always do this. Number two is usually easier, but you're restricted to circuits that only have independent sources. Okay. And then I see the question in the chat. So we can place something in between A and B with 5 different objects, I'll say circuit elements, instead of trying to break down a complicated circuit once we find the values of VT and RT. Yeah, I'll say this, that if I take this circuit, let me circle it here. So this is the answer. This is the Thévenin equivalent right here. That's the Thévenin equivalent circuit. If I put this in a box and I bring 2 wires out, right? I bring 2 wires out, A and B, and I put this in a box, right? I put this in a box, and they're the same size boxes. You can't tell the difference. And I expose terminals A and B. And I give you a voltmeter, an ammeter, a power supply, maybe a voltage source, current source, and you connect things to these outputs, A and B. You would not be able to tell which is which. Both of these circuits would behave the same from the perspective of V versus I when you connect sub-circuits or circuit elements to those. They would look exactly the same. As long as you have the correct VT and the correct RT calculated for this circuit. All right. Okay. If you have questions about that, let's explore those during office hours, and we'll talk about that. So what I want to do now is I want to bring you back to the slides so I can show a concept here, the concept of maximum power transfer. Okay. Okay, so maximum power transfer, or talking about power delivered from a source to a load. So suppose you have a realistic source, and by realistic source, I mean it's non-ideal. And non-ideal means it can be represented not with just a voltage source, but a voltage source of with a Thévenin resistance. Batteries can, in a way, be modeled like this. This would be the internal resistance of a battery. So you want to transfer as much power from this realistic source to this resistive load. Okay, so for example, let's say you have an audio amplifier connected to a speaker. You could model that audio amplifier as a voltage source and AC source connected to a resistor. The resistor would be the load, or some kind of sensor that outputs a voltage to a data acquisition device. The sensor would be this source. The data acquisition device would look like the load. An electric guitar to an audio amplifier input, or guitar amplifier input. The guitar would be the source. The amplifier would be the load. Okay, or an radio frequency antenna connected to a receiver. That's another example. So, and so why would you want to do this? You'd want to do this because in general, you want, if you have some kind of especially weak sources like an antenna, like a sensor, or you just want to get the most power delivered to the load, this is a good thing to do. So to figure this out, how do you maximize that power? First, consider the power is VL times IL. Here's the load current and the load voltage. By Ohm's law, you could calculate IL from VT and the 2 resistor values. Right? That's just Ohm's law. Using voltage division, I could calculate VL, right? Because I have series resistors. VL is VT times RL over RT plus RL. I multiply these two together, IL times VL, and I get power delivered. So that's power delivered right there. It's just this times this. I get that. All right. So now let's figure out, how do you maximize this? How do I maximize P sub L? Well, if I have this circuit, let's look at the extremes. Let's say you have the case where you have a source, you have this realistic source, you know VT, you know RT, and RL is variable. Like the case I mentioned, you can use maybe a 4 ohm speaker, an 8 ohm speaker, 16 ohm speaker. How do I get maximum power transfer to that speaker? I can change the load resistance. If you look at the extremes, we do this table, right? Look at different RLs, figure out what VL, IL, and PL are. Let's go to the extremes. What are the extremes of RL? 0 ohms and infinity ohms. Like, let's see what that gives us. If you have RL equal to 0 ohms, you've just shorted across your terminals. VL is going to be 0. IL is going to be non-zero. It's going to be the short circuit current. But 0 times anything is 0. So if you have a 0 ohm resistor, you get no power delivered. If I change that to infinity, the other extreme, I get 0 current. That RL is an open, and you get no current. So 0 times whatever the voltage is, the open circuit voltage, is 0 watts. So that doesn't really narrow anything down. That means the answer is not 0, it's not infinity, it's somewhere in between, but I wanted to show those examples. So you could take a calculus approach. The calculus approach is, remember how to find a maximum when you have a function? Like we're looking at PL versus RL. We're changing RL. We're trying to find a maximum. PL versus RL. So take the derivative with respect to RL. DPL, DRL equals 0. And then solve for RL. That will tell you where the slope is 0. So you can find maximum or a minimum. You'd have to check the second derivative to figure that out. But instead of working through this and proving this, let me show you graphically, because I think it's more impactful. Let's use an example where we have this circuit, this realistic source, 10 volts Thevenin voltage, and 100 ohms Thevenin resistance. And I connect a load resistor. So I have this source, it's specified. That could be, by the way, that could be like any circuit, any linear circuit with sources and resistors that I've represented with these two components here in the Thevenin equivalent. I connect a load resistor, and I'm going to vary that load resistor. I'm gonna maybe take a potentiometer and vary it from 0 to something big. And I plot, and I calculate power using the voltage and the current I measure through this resistor. Well, if I plot that, then I get this. This is the power delivered to that resistor versus that resistance value in ohms, right? So this is the value of RL, and this is the power delivered to that RL resistor. And so you can see there's definitely a trend here. You have a peak, but notice down when RL, down at the bottom, when RL equals 0, you get 0 power. That makes sense from what we showed in that table on the previous slide. And then as you go off to infinity, power falls, and as RL approaches infinity, the power goes to 0. But you can definitely see this peak here. And notice where that peak happens, right? That peak happens right here at 100. So isn't that interesting? You have 100 ohms here, and RT is equal to 100. So what you will find if you take the calculus approach, or if you do enough of these, is that maximum power transferred to that load resistor, occurs when the load resistance equals the Thevenin resistance. So the takeaway is, for maximum power transfer, set RL equal to RT. So if you have some kind of device, you have an audio amplifier, and it says output impedance. We're going to talk about impedance, but it says 8 ohms. Then you want to connect an 8 ohm speaker to that amplifier to get maximum power transfer. If you have an RF radio frequency receiver and it says 50 ohms, it's the load, then you want to connect that to a 50 ohm antenna. Okay, you want the Thevenin resistance to equal the load resistance to get maximum power transfer. Okay. So that's in general another takeaway from the Thevenin equivalent topic is the Thevenin equivalent gives you a simple way to represent a more complicated circuit from the perspective of the outside world. And it also tells you, well, if I were to connect a load to those two terminals, a resistive load, what resistor value do I use, or what resistance do I apply to get maximum power transfer to that load resistance? Okay. All right. So what I'll do now is I saw the request to go back to the last slide. If you'd hold that off to office hours, then please join me there. We'll go back to that. But in closing, since I hit the wall on time here, um, we have 2 quizzes, a couple quizzes, and a homework due coming up soon. Check those due dates and due times on Canvas. The exam will be next Wednesday. See the announcement that I will be sending out. There are review problems and practice problems. Check those out. Go ahead and post to the Slack workspace under the exam channel if you'd like to do that. Thanks for joining class. If you'd like to join office hours in just a few seconds, then stick around. If not, I'll see you next time. Have a great night.